All right, so in this video, I'm going to go over an example problem involving rotational kinetic energy and angular momentum. So this is a good first video to watch after you watch the introductions to these topics. It's a simple problem, and it's good to just get the feel for the numbers and sort of how the equations play out. So go ahead and watch this one after you watch the two intros. And let me just open up the problem itself. So if you want, pause the video, read it more carefully, but the basic problem is this, is that we want to calculate the angular momentum and the kinetic energy of the Earth, and they give us the mass of the Earth, and then they give us the radius of the Earth in this problem. Then they want us to compare this with the total energy uses of the United States in 1 year. And so let's go back to stop here. Okay. And so, well, let's just start with angular momentum. Angular momentum is given by L is equal to I times omega. L is the angular momentum, I is the moment of inertia, omega is the angular velocity. And so in order to calculate the angular momentum of the Earth itself, I just need to know these two quantities, the moment of inertia and the velocity, angular velocity. The angular velocity is easy. I have a useful formula for that, which says it's equal to 2 pi over the period t. What is the period here? Well, the period is how long it takes something to happen. What is that something? Well, it's how long it takes it to rotate once. And so we just need the number of seconds in 1 day. And that works out to be 86,400. That's how many seconds there are in 1 day. And so if we plug that in, then we just say 2 pi divided by 86,400, we get our answer. And so this would just be 2 pi over 86,400. And I ran out of room, but the units are radians per second. And so now we just need to know the moment of inertia. Well, the moment of inertia depends on what kind of object you're looking at. And we're looking now at the Earth, and so we can kind of approximate that as a uniform solid sphere. And so what is the moment of inertia for a uniform solid sphere? Well, it's I is equal to 2/5 times the mass of the Earth times the radius of the Earth squared. And so we just need to plug in the mass and the radius squared there, and we'll get our moment of inertia. And then when we put these two quantities together, multiply them together, what do we get? Our final answer is going to be 7.13 times 10 to the power of 33 kilograms times meters squared per second. It's a really big number. We should expect it to be really big because the mass of the Earth is really big. So let's take a look then at the rotational kinetic energy. Let's see how much we have there. Well, the rotational kinetic energy, K, I write it as KE subscript ROT for rotation, that's equal to 1/2 times the moment of inertia I times omega squared. And so what happens when we plug these values in? Well, we still have the same moment of inertia. We have our omega squared, or we have our omega, and we can just square that to get omega squared. But what we're left with is 2.6 times 10 to the 29 joules. So it's 2.6 times 10 to the 29 joules. That's a lot of energy. In fact, if we compare it, if we go back, because the last part of the question wants us to compare it to the total energy used in the United States in 1 year, that's 10 to the power of 19. This is 10 to the power of 29. So it's a factor of 10 billion more. So the rotational kinetic energy is 10 billion times more than the total energy usage in the United States for 1 year. All right, so that's our first problem. We'll make another video with a little more complicated of a problem, but that's it.